So this mini course is about the homotopy theory of strict omega categories. Strict omega categories. So there will be 3 sessions and 3 parts. In the first part, I'm going to present a equivalent model structure on omega cat. So equivalent model structure on cat omega, the category of strict omega categories. In the second part, trying to characterize the cofibrant objects in this model structure. So this will be about polygraphs and cofibrant objects. And finally, I'm going to apply this machinery to the homology of monoids. So application to the homology of monoids. So that's the plan. So I expect everybody knows probably a bit of model categories. So I'm not going to prove statements, general statements about model categories. I'm really concentrating on this specific case on omega cat, although I'm going to remind you the statements I will use. If you want proofs, then there are, of course, many references, classical references. So about model categories, among all classical references, of course, you have the first text by Quillen, Homotopical Algebra. Homotopical Algebra. There's a book by Hovey on model categories. I will also use something that may be a little less classical. It's a paper by Tibor Beke called, I believe, Chiffrifiable homotopy. Let's get the reference, the exact reference. Chiffrifiable homotopy model categories. Homotopy model categories, and that's in 2000. So this contains a theorem that proves absolutely crucial to the proof of the model structure on omega cat. So, but that's again pure model category theory. Okay, so to start with, so I start with a few preliminaries. To fix the notations I will use throughout. First important point is to get used to lifting properties. So lifting properties. So you have a category C. And if consider a commutative square like this, and here morphisms F, G, U, V. You say that F has the lifting property, lifting property with respect to G if there is a morphism K making both triangles commute. Okay. And of course, dually, you say in the same case that G has the right lifting property with respect to F. So G has the right lifting property with respect to F. If we have this, then we will denote F pitchfork G, like this. And whenever you have a class X of morphisms, we shall denote by this the class of morphisms who have the lifting property with respect to all morphisms in X. So F such that F G for G in X. Of course, the dual notation is clear. Okay. Now, where am I? Yeah. Okay. Oh, sorry. I'm still breaking the law here. Okay. So for the record, if you have a set of morphisms I, then those maps will be called those ones. Sorry, will be called I injectives, and denoted like this. And classes who are defined by lifting properties have traditional formal properties, purely formal properties. For instance, whenever X is a class of morphism, then a class like this is always closed by push-outs, sums, retracts, transfinite compositions, transfinite compositions, and the X on the right is of course closed by pullbacks and so on, products and the dual properties. We always assume that the categories we work in are complete and co-complete, so I won't mention it throughout the course. It's always complete and co-complete. Okay, that's it. So now, another point is we want to get factorizations of any morphism. We say that an object X, object A, is small in C if the Hom functor here preserves countable directed colimits. We only deal here with the countable situation. We're not going to mention higher cardinals, because in the model category and omega cat, we only have to look at countable chains of morphisms. So now, when you have a set I of morphisms, such that the domains of these morphisms, so I is a morphism in I, for instance, so the domains here is small, with small domains, small domains, then you can apply the small object argument, small object argument, meaning that any morphism F from X to Y in C can be factorized in two morphisms here in such a way that, so Pi, say, such that P is in I injectives, I inch, and I is in what I called I cof, which is the morphisms who have the left lifting property with respect to all I injectives. Okay, so that's purely formal, and we shall use this in our situation, particular situation. Now, okay, one more general notion of weak factorization system. Weak factorization system. So you say that you take a category C, two classes of morphisms, left and right here. So we say that this pair is a weak factorization system for C if first every map in C, each F factors as R L, with R in R, L in L, and L is exactly the set of the class of maps having the left lifting property with respect to R, and R is duly this class of maps. So when you gather all this together, you get that if you're in your category C with a set I of morphisms with small domains, then these two classes build a weak factorization system for C. So that's the general situation here. Now we can come to model structures. There are many different ways to describe the axioms for equivalent model structure on C. For instance, one is to say that model structure on C, you get three classes of morphisms, W called weak equivalences, let's say cof called co-fibrations, fib fibrations, and you ask this. The following properties. So W is supposed to have the 3 for 2 properties, meaning that whenever you have F, G, and the composite H, G, F, if two of those maps belong to W, then the third also belongs to W. You ask the classes W, cof, fib to be stable by retracts, stable by retracts. You ask that whenever you have a square like this, commutative square, with this map I in cof, pictures like this. This map here, P in fib. If this one is also a weak equivalence, then there's a lift here. And duly, if this one is a weak equivalence, then there's also a lift. So that means simply that cof into W belongs to fib left, and cof belongs to fib enter W left. And finally, we ask for each morphism F, each F, X to Y, factors in two ways. That is, either you factor with a fibration, which is also a weak equivalence, called trivial fibration, composed with a cofibration, or a trivial cofibration composed with a fibration. So you have this. So that simply means in the previous terminology that you get two weak factorization systems in your model category. Namely, trivial cofibrations with fibrations, or cofibrations with trivial cofibrations. Okay, so that's one of the possible definition of what a model category is. It's not the one we shall use. The one we shall use is proved in Baker's paper. So there's a theorem by Jeff Smith telling that in order to get a model structure in this sense, it's enough to have in your category the following data, which I will keep here because the main the plan is to check those conditions in our particular case of omega cat. So I will keep the Smith conditions all the way here. So those conditions are, first, the same as this, W has 3 for 2, and stable by retracts, plus stable by retracts. Second, there is a set I of morphism such that the I injectives belong to W, to the weak equivalences. The third condition is that I cof, that is this class of morphism, intersected with W, should be stable by push-out and transfinite composition. Stable by push out and transfinite composition. In our case, we basically only need countable composition, as I said before. And the fourth condition is the so-called solution set condition. It's slightly solution set condition. So what's this? It means the following. When you have a map I in this set I, A, B here, a weak equivalence here, F in W, and a commutative square like this. Okay, no, let's go back a few seconds. For each I, in I, there is a set called, say, Ji, if you want, a set of maps such that each square like this factorizes with a J in this Ji. Okay, that's solution set condition. And I leave these conditions here. And so it's a theorem of Jeff Smith to the point that if you have a complete and co-complete category together with a set I of morphisms satisfying those conditions, then you get equivalent model structure by defining, so if the category C satisfies conditions 1, 2, 3, 4.
Sorry. So here it's for every F, or
no. That's why I was. It's you have I is given, okay, and to each I you have a set Ji. This set is independent of F, of course. Okay.
And the set is
okay,
non-empty.
but. Excuse me?
And the set is non-empty, otherwise the condition...
No. It's a what? Oh, I'm sorry, I missed something. Of course you need... thank you. Of course you need some condition on Ji. Ji is in W... Of course, you need, of course, well, otherwise it doesn't make sense, of course. Yeah, thank you. But what's important is that set Ji, so Ji is, consists in trivial cofibrations, okay? So meaning, but in our case, the set Ji will consist of a single morphism. For each I, we get a J, such that this commutes. Okay, so it boils down to something slightly simpler. So the theorem by Jeff Smith says that if C satisfies these 4 conditions, then if you define the cofibrations as the I cofibrations, that is this, and of course, fibrations are those, then you get a model structure in this sense here. Then if you set the cofibrations as those maps, then W cof fib is a model structure. Okay, so much for the general model structure properties. Okay, so by the way, this theorem is the main point of this paper here. So proof. So I'm not going to prove this here. I just refer to this paper where it is completely proved. Okay. So it's time to get to let's take this one. Okay. Okay. So let's enter the central object of the course, which is the model structure on cat omega, strict omega categories. So I'll be more precise here. As for omega categories, the primary source is, of course, Street's paper of 1987, The Algebra of Oriented Simplexes. Simplexes, okay. Where all these definitions come from. So again, I need to fix the notations. So I'm going to record things that probably you all know quite well. So you start with the small category of globes. It's category O. Its objects are integers, 0, 1, 2, and its morphisms are generated by pairs of morphisms call it sigma and tau, subject of the following conditions. You ask sigma equals tau sigma, and tau sigma equals tau. So those are the small globes. Intuitively, these objects you can visualize as little pictures like this. 0 would be this, 1 this, 2, something like that, 3, something like that, and so forth. And the morphisms sigma and tau are the inclusions in the source and targets at each level. Okay, so that, for instance, source takes this here, and target takes this here. Here. Okay. So these are the globes. The set of globular sets are presheaves on O. So O. That is functors from O to contravariant functors from O to Z, so O up to Z here. And a strict omega category I never okay, so now a strict omega, so cat omega, the objects are C's. So C is a globular set, and it's equipped with composition operations. Okay, sorry. So an omega category, so it's here you get a certain globular set with source and target maps, C0, C1, Cn, and so forth. And whenever you can compose, if you have two cells, n cells here, x, y, if let's S n minus 1, the source of y equals the target of x, then you can compose x and y here. I systematically will write the composition in the diagrammatic order. Okay, so that if I have two one cells x, y, the composite will be denoted by this. And also each cell has an identity cell of higher dimensions. So if x is in Cn, then there's a cell identity n plus 1 of x in Cn plus 1, acting as an identity for the composition operations. So let's make a few pictures to get this straight. So these compositions are subject to different axioms. Associativity. Compositions are associative. Associativity. They satisfy the exchange rule, meaning that if you have 4 cells here, X, Y, Z, T, and those cells compose along a contact of dimension I here, and here a contact of dimension J, then both composites are equal, meaning that in our notation we will write something like X, J, Z composed vertically with Y, J, T is equal to X, J, X, I, Y, J, Z composed in dimension I with T. Okay, exchange rule, plus rules of identity, rules, which simply explain that identities do what we expect them to do, of course. Now, by its very construction, we have a forgetful functor from omega cat to globular sets. This one has a left adjoint here, so to each globular set you can consider the free omega category generated on this set. And among those free objects, we'll be especially interested in the objects here that come from the representables in O hat. Those we denote by ON. So ON is the N globe. ON is the N globe. It's the N globe, and it's the image of the N representable in globe. So the picture of the N globes is what you expect. O0 is just a point, meaning, of course, that in omega cat you see it as an omega category with only one zero cell and identities in higher dimensions, of course. So O1 you can represent as this, O2 like this, and so on. And besides these objects, the globes, you have the spheres, which I call delta O n. Delta O0 is simply empty. It's the empty category. Delta O1 is just 2 points. Delta O2 is this, and so on. So the deltas have the same cells as the ONs, except for the higher dimensional one. So geometrically, you think of ONs as disks and delta ONs as spheres. As spheres. Another important point, so a crucial feature of omega cat is that it's enriched over itself. So that's really what makes the whole machinery work, as I hopefully will show you. Cat omega is enriched over itself. What does it mean? Simply, when you get, imagine C here, an omega category, take two zero-dimensional cells in it, X, Y, then there's a Hom set, which I denote by brackets like this. So this will denote the Hom set of X, Y, of 2 points. And the point is that this Hom set is itself endowed with the structure of omega categories. So this is an omega category. You see that, for instance, if you take, for instance, a 2-cell in C, here, in this Hom set, then it becomes a 1-cell in this category here. This process I denote with brackets. That's it. If I take U certain n+1 cell in C, then you get, and of course with appropriate source and target here, that is the zero source is X, the zero target is Y, then you can associate to U bracket U, which is n cell in this category. So it belongs to X, Y, N, if you want. So this operation will be. Is that right?
I'm puzzled about what you're saying. I mean, to say that the category is enriched over itself is to say that it's monoidal closed.
No, it's.
That's not what you're saying.
No, I'm just saying that the Hom set is itself. So cat. It's true. Cat omega is, well, the monoid structure is simply the Cartesian product here. Okay, so with Cartesian product, you get a monoid structure on omega cat, and so you can consider categories enriched in omega cat, and it's a fixed point. It's a fixed point. Because you have cat n+1 is cat n cat, okay? And when you go all the way to the limit, then cat omega is cat omega cat. Yeah. It really is enriched over itself. Well, maybe it's not the appropriate way of saying it, but it's yes?
Basically, you have a 2-point suspension functor, which takes you to bipointed. You have a 2-point suspension functor, which takes you to bipointed strict omega categories, and it's right adjoint as that Hom functor that you're talking about.
Well, yes, yeah. Okay. So but what's important in what I'm going to show is this operation here, this operation, because this is really what makes all the argument work, is this possibility to jump from one dimension to another. I will illustrate this point in a few lemmas. It's in a moment. Just here to set the notations. Okay, so you get this Hom set, which is itself, and this respects the compositions. Okay, so it's a certain when you compose here two cells, two cells against a border of dimension 1, then in X, Y, you basically compose two 1 cells against a border of dimension 0, and so on. Okay. And so that's it. Which one is this? I never. Yes. Good. Okay. So we're almost ready to define the model structure of the title. It is almost time to do that.
Excuse me.
Yes?
Maybe I lost the point. This is the operation you take n plus 1 cell.
Yes.
And you associate with this what?
An n cell in you have.
Who are x and y?
No, two. Okay, this is the category you start with. Okay, that's C, an omega category. So this C has cells of all dimensions: C0, C1, C2. Okay, and I pick two 0 cells. Okay, X, Y, in C0. Okay, and then I may consider all n cells in C, all cells in C, which have as 0 source X and 0 target Y. So one example is a 2 cell which looks like this. Okay, all I say is that to this 2 cell, now we can consider another omega category, X, Y. So the cells of this category are simply all cells in C which start in X and end in Y. Okay? And there's, you can associate to each cell here in X, in a cell of 1 dimension less in this. So this this operation lowers the dimension by 1 systematically and respects compositions, identities.
Itself, but seen as a...
Yes, exactly. Everything you want. But this is it's good that you point the question, because it's really the most important feature of omega cat in order to get all these conditions here. Basically, all the proofs will be based on inductions using this back and forth going between the Hom set and the starting category. Okay, so let's describe now the model structure I want to present. So I told you about ON, about delta ON, so the n sphere and the ON, and of course there's a canonical inclusion here, IN. It's a morphism of omega cat. For n equals 2, it simply takes, for instance, this picture and inserts it in the 2 globe like this. So that's an example of I2. So that's I2. And first part of the model structure is, according to Smith's theorem, to pick an I, and I is simply this set of morphisms. Okay, so those will be the generating cofibrations in omega cat. Generating cofibrations. Okay, so that's good. I didn't define the weak equivalences, which are the most important part of the structure. So for that, we need something. We need to put some relations on cells in omega cat, and the basic definition is that of reversible cell. Reversible cells and omega equivalence relation. Omega equivalence relation. So this definition seems a bit strange when you see it in the first time. It goes like this. You say that take a cell U, could be any dimension. I represent in dimension 1, but it's just to make a picture. So you say that U from X to Y is reversible. Reversible if there exists a cell in the other direction, if there is U bar from Y to X, such that the composites here, so that's U bar, U composed with U bar. I don't put the dimension here. It's the dimension that's obvious from the context. So this is omega equivalent to the identity on X. And of course, the other is omega equivalent to the identity on Y. But I didn't say what omega equivalent is, of course. Omega equivalent says that two cells, two parallel cells, X, Y. Parallel means same source and same target. X and Y are omega equivalent if there is a reversible set U, if there is U from X to Y reversible. So this definition is not a joke. It's not circular as it may appear. It's a definition by mutual co-induction of the concepts of reversible and omega equivalence. If you're not, so what it means exactly, let's, so, which one is this? This one, yes. I'm going to permute 2 here. Okay. And this. Okay, it simply means this. what's a reversible cell? To get a reversible cell, to check that U is reversible, you have to build an infinite tree of cells of higher and higher dimensions on top of I. So you first have to get a new bar here, and then you have to get cells here and there, from the composites to the infinity, so one dimension higher, and so on. So you repeat the process with those two cells. So being reversible simply means that there is an infinite tree like this. In other words, what you say is, suppose you have your, so S is a set of cells, for instance, and what you do is you consider a certain set of cells, and you attach to X 3 cells, I of X, the inverse, which is the U bar here, okay, and L of X, right of X, which will be those 2 cells here, L of X, right of X. So to each cell you associate 3 cells, and that's a co-algebra of this functor here. And if you take the union of all the carriers of all these co-algebras, so of course you put the equations, okay? So you ask for Ix to go in the right directions, and these cells here to go from the composite to identities like this, okay? So you take all these co-algebras, you take the unions of the carriers of all those, and that's your reversible cells. That's your set, your class of reversible cells in your category. So now, how do you prove that certain cells are reversible? So that's by co-induction. What you prove is just that you just have to take a set X and imagine all you have to build is a co-algebra like this, is to attach to each cell in X a triple of cells in X3, okay, such that the conditions are satisfied. Okay, but once you're convinced that it's logical, then you can write proofs in quite a very light manner. So you write your proofs by so-called co-induction. So for instance, an example of reversible cells are the identities. Why are identities reversible? Simply because to each identity cell, you can associate Ix, which is the same, and both identities on both sides here. So you get a particular co-algebra of your functor, and it proves that, by definition, this set X is included in the set of reversible cells. Okay? And once you get the idea of reversible cells, then of course you get the idea of omega equivalence, which is, again, the concept that 2 cells here are omega equivalent if you can put a reversible cell between those cells. So why do I speak about that? Simply because this idea of reversible cell and omega equivalence permits the definition of weak equivalence. No, not this one. This one, maybe? Yeah. Not this one. Okay. Okay, now for the definition of it. Okay, now it's time to define W, the weak equivalences of our model structure. So we say that F from C to D is a weak equivalence if the following holds. In dimension 0, for each cell D in D0, there is C in C0 such that, so it's not properly surjective, but it's surjective up to omega equivalence, meaning that FC is omega equivalent to D. So it pictures like this. Okay. C, D here. If you pick a D here, then there's a reversible cell from FC to D. And in higher dimensions, the definition goes like this. If you take two parallel n cells in C, so if X, Y are in Cn and parallel, meaning same source and same target, and if there is a cell W going from Fx to Fy, then there is a cell, there is V from X to Y, such that Fv is omega equivalent to the original W. The picture is like this. You have C here. You take two cells X and Y like this, and you suppose that the images Fx, Fy are connected by a certain n+1 cell W, then there is a V here such that F of V, the image of V here, F of V is omega equivalent to this W. So those are the weak equivalences. Okay.
So you don't have any faithfulness?
No. What do you mean?
The first one is somehow like essentially subjective.
Yes.
The second one is like full. And you would expect faithful.
Well, it will be a consequence of that there's a certain, weak equivalences are injectives and Hom up to omega equivalence again. Okay? Yeah, that's right. That's right. So that's the important definition. Which one is it?
That's the lifting property, right?
Excuse me?
That's the lifting property, right?
It's a lifting property with respect. It can be explained as a lifting property, but only after we define those J's here. You see? So what has the lifting properties on the nose are the trivial fibrations. I come to that in a moment. Okay? Okay. Yes, I know. I didn't. Yeah. So those are so I get my I and my W, and now we have to prove all these properties here. Property 1, there are 2 cases which will be quite easy, and one much more difficult. 2 is now the easiest part, okay? 2 is the easiest part. Why? Because what is I inch? It's, as you said, defined by a lifting property. So what is a map in I inch? That will be our trivial fibrations. It's a map that has a right lifting property against all INs. Okay, remember, those are delta ONs over N here, X, Y. But what does this mean? This simply means that for N equals 0, it simply means that P0 is surjective, okay? And for higher N's, this simply means that if you get 2 parallel cells here in X prime here, and there's a cell here filling the hole between px, and px prime, W, then there is exactly a cell here, V, such that now FV really equals W. But we saw that equal cells are omega equivalent, so identities are reversible. So that's why clearly I inch is in W. So this one is checked. Okay, this 2 here. That's the easy one. Easy one. Now, as for 3 for 2 for W, so we first consider F G X, Y, Z. Okay, the first case is easy. If F and G are in W, then H is in W. Why is that? That's simply because the notion of omega equivalence is a congruence. It respects everything you want, okay? So it respects compositions, it respects you can remember that so this relation here is a congruence, is a congruence. Okay, so it's an equivalence relation. Okay, so it's, for instance, reflexive because identities are reversible. It's symmetric by definition. Transitivity needs a proof. Okay, and again, this proof will be by co-induction. Okay, and the congruence simply means that if you have two omega equivalent cells and you pre-compose, for instance, by another cell of any dimension, then the composites are omega equivalent, and the same on the other side. So this implies immediately this first case. Okay, second case. You suppose that. So I never. Which one is good one? Let me not. Good one. Good one. Yes. You suppose now that H and G are in W. If F, G are in, if G, H are in W, then so is F. Then also F. So this is not really difficult either. I'm going to show it. Okay. Okay. Celui du O. Yes, why is that? So the picture is like this. You have, say, C, D, E. Yeah. Just make a little drawing. C, D, E. And you suppose that this one is a weak equivalence, and this one too. Now, if you take two, so I skipped the dimension 0, left it as an exercise. In high dimensions, what do you have? You have an x here and a x prime here. And you suppose that here you get fx prime, a certain w here. And you want to lift this w up to omega equivalence between those here. But then you apply G here. You apply G, and you get GW, so that's between HX and HX prime. You use the fact that H is a weak equivalence. This gives you a V here, that is sent by H to a certain HV, omega equivalence to GW. And here we come to the faithfulness property up to omega equivalence of F, which we can prove. I'm not going to, I'm running extremely late on time. I didn't say half of what I was meant to say, so I'll skip that, but you can imagine that the tricky part is to get a V here. Okay, once you get a V, then to prove its properties is easy. Okay, it's just following the definitions and can be reasonably left as an exercise. However, so what we get here, we get two cases here. We checked two cases. In the remaining time, I'll just show you why the third case is much more complicated. What's the problem and how we're going to fix it. Let's get it. Okay, so the third case is nasty for this reason. So, again, you have F, G, and now you suppose that, so let's get another picture like this. And so here is F, here is G, and here is H. And now what you suppose is that H is a weak equivalence and F also is a weak equivalence. And you want to show that G is 1. But now the problem is as follows. You take two cells here, say y prime in D, and you suppose that here you get on between jy and jy prime a certain cell W. Okay, now the problem is, how do you lift W here? You can't, because to use the lifting property of weak equivalences, you have to get first parallel cells here that are sent to the border here. So the difficult part is to get here a cell. It's not about checking its properties, it's just where it is. How can I build such a cell? In order to do that, we did a completely new ideas. So we need to introduce cylinders. N cylinders. So I just, yes? No? Sorry. So unfortunately, I don't have the time to, I do that tomorrow. The cylinders, I just give you a little pictures of what's going on. You need another construction. So the construction goes like this. If you have an omega category C, yeah, strict one, you can associate to it another omega category, gamma of C. Gamma of C, this will be the category of small cylinders internal to C, if you want. Okay? Small cylinders internal to C. What does it mean? Just the following. You have to say, so this has to be an omega category. So first you have to say what are the cells. Okay. So the zero cells, what's a zero cylinder, for instance? A zero cylinder is simply a one cell in C. Okay. Okay, one cell in C. If you get two 1 cells, not parallel this time, you get two 0 cylinders. And to get the idea of 1 cylinder, what's a 1 cylinder? It's the data of a cell here, and a 2 cell connecting the 2 borders here. So that's a cylinder of dimension 1, okay? Cylinders of dimension 2, cylinders of dimension 2, you get 2 cylinders like this, so one like this, one like this. You will ask them to be parallel, so that in this setting, this will be the source of this cylinder, and this the target. So 2 cylinders of same source and target will appear like this. So like there's a hole inside, of course, here. And the 2 cylinder will consist in putting a top here, a bottom here, and in between a 3 cell connecting what has to be connected, and so forth. So the main part is to prove that those cylinders consistently define another omega category. Something I forgot, this version of cylinders we use here are so-called reversible cylinders. So we will ask in addition that all vertical cells have to be reversible. Okay, so that's important. There's another notion of cylinders where you don't ask that, but in our setting, we shall need that. So I think I stop here because it's time, exactly time, and resume tomorrow.